Okay, let's begin. Welcome everybody to this fixed Majorana-Raychaudhuri seminar series. Today's speaker is Lorenzo Calibbi, and he's going to talk about testing Frogatt-Nielsen flavor models with gravitation waves. And maybe I will send you a reminder when 5 minutes are left.
Thank you. Thank you for the invitation. It's a pleasure to be here. Yeah, I will be talking about this recent paper written in collaboration with Simone Blasi, who is currently at DAISY in Hamburg, and Alberto Mariotti and Kevin Turbang, who are from Brussels, from VUB Brussels. Well, the motivation is the fact that compared to other sectors of the theory, the flavor sector of the standard model is far less well understood, in my opinion. Well, not only my opinion, kind of a common law, in the sense that there is no principle, no guiding principle as strong as, for instance, the gauge principle that sets the interactions of the standard model particles with the gauge bosons. And the very fact that we observe three families, three generations of standard model quarks and leptons is kind of a mystery. So there is no fundamental reason, as far as we know, why it should be like that. And the stuff we're made of is just here, the first generation. So why there are three? And more importantly, why they exhibit such hierarchical patterns in their masses. Is this just an accident, or this structure hints of some unknown dynamics, some new physics at some energy scale higher than the electroweak scale? So we don't know. So in particular, we can parameterize this our ignorance, in a sense, because the flavor sector comes from this part of the standard model Lagrangian, from the interactions of the standard model fermions with the Higgs field. So this coupling here, the Yukawa matrices, can be in the standard model are just free parameters. So even without considering the neutrino sector, you have 13 free parameters here that the best you can do is just set to the suitable value to account for the observed quark masses and mixing and charged lepton masses. And as I was mentioning already, still it looks like they are not just random numbers because they exhibit some hierarchical structure in the masses and also in the quark mixing. So the famous hierarchy of the mixing angles in the CKM matrix. So it has been in a way a long-term dream for particle physicists to try to explain these numbers in terms of a more fundamental theory. And long ago, already more than 45 years ago, a paradigm based on flavor symmetry has been proposed. One of the, as far as I know, the first of such kind of proposal was introduced by Frogatt and Nielsen already in '79. And the idea is basically charging the standard model fermions under a new symmetry, a new flavor symmetry. So the role of this symmetry is basically forbidding these terms here at the renormalizable level. So if the symmetry is unbroken, you cannot write these terms in the Lagrangian, with the possible exception of the top Yukawa, since it's the only order one number that you have there. So which means that then the fermion masses arise once this symmetry, this flavor symmetry is broken spontaneously. So you have to introduce a scalar field, like a Higgs field for the flavor symmetry, whose VEV or VEVs, if you have more than one, break the symmetry spontaneously, such that the Yukawa interactions arise as higher dimensional operators. So this is what happens in schematically. So basically, instead of having renormalizable Yukawa interactions, your Yukawa interaction will be proportional to some dimensionless couplings, which usually are just taken as structureless, so just flavor anarchical, order one coefficients. So they are not responsible for the hierarchies of fermion masses and mixing. And a certain number of insertions of these flavor breaking, symmetry breaking VEV over the cutoff, over energy scale that sets the UV completion of the theory. So basically, these exponents will be dictated by the symmetry in a suitable way, such that here you can obtain small numbers, like the up quark mass, which is several orders of magnitude smaller than the top mass. So the idea is that the VEV that breaks the symmetry is somewhat smaller than the cutoff. So this ratio is a small expansion parameters. This exponent can be rather large, so you obtain the hierarchies. So as you can see here, I didn't say anything about what kind of symmetry does this job. And over the years, many options and many explicit models have been proposed. And in general, still keeping this schematic structure, the symmetry could be abelian or non-abelian, continuous or discrete, could be a global symmetry or could be gauged. So what I'm going to talk about today is the simplest possible option, simply introducing a new flavor charge in a way, so a U1 symmetry, so a continuous abelian symmetry, which was, by the way, the original proposal by Frogatt-Nielsen. So the idea, so unlike non-abelian symmetries here, you would not really explain why you have three generations. It could be better done if, for instance, you have some non-abelian symmetry where you can have a triplet. So when you can arrange the three generation in the same representation. So in this case, we are not going to be that ambitious. We are just introducing U1 charges for the standard model quarks and leptons. Here I'm just showing the quark sector. And of course, the idea is that the symmetry distinguish the three generations. So up quarks, charm, and top will carry different charges under the flavor symmetry. So you want to write these terms as formal invariant under the symmetry. You need to introduce a certain number of insertions of this flavon. That's the usual name for this scalar field that breaks the symmetry, that of course needs to be charged. So you see that given this structure, then the Yukawa coupling will appear as the entries of these matrices will appear as exponentials where you have these small expansion parameters, and the exponent will be given by the charges of the standard model fermions. And then this allows you in general to fit your observed fermion masses and mixing, because what you do is just, as usual, rotating these matrices into the fermion mass basis. So applying B-unitary transformations to diagonal Yukawa matrices, and these rotation matrices, these unitary rotation matrices will turn out to be given again by small numbers controlled by differences of the charges of different generations. And by the way, this independent on how you, what are the specific charges you're giving, just because of this structure is giving you as a first order a successful prediction for the structure of the CKM, in the sense that the 1-3 mixing will turn out to be, as we observe, of the order of the 1-2 mixing times the 2-3 mixing. If you then want to fit the observed quark masses, you can give charge assignments like this. This is an example. So as you can see, typically you need larger charges for a lighter generation. So you have a higher suppression here. So you get a smaller mass. And of course, this is just at this level an order of magnitude prediction, because you still have freedom of adjusting these order 1 coefficients. So the theory, this model does not really predict what these numbers are. So they are just related to the fundamental couplings in the UV completed theory, where you will basically open this blob and introduce some fields like vector-like quarks charged, so under the standard model gauge group, that will mediate the flavor breaking to light quarks. So these order 1 coefficients will be basically come from the from products of the fundamental couplings of the UV theory that lives at this higher scale lambda, and which I'm not going to specify today. So you get the right hierarchical structure, and then with those order 1 coefficients, you can fit precisely the fermion masses and CKM angles. So you can do the same in the lepton sector. Of course, you have to specify how neutrinos get mass. Here, to be agnostic, we are just assuming Majorana neutrinos, so just introducing the Weinberg operator. So that will be suppressed by another scale, that is the lepton number breaking scale, maybe related to the seesaw mechanism, so to the mass of right-handed neutrinos, or to something else, we don't know. But anyway, as you can see, the structure of the neutrino masses will be still just controlled by the charges of the left-handed leptons, of course. So one way then to account for the large mixing in the neutrino sector is just to taking an anarchical neutrino mass matrix. So basically charging the 3 left-handed leptons in the same way under this U1 symmetry. So you see in this case, it's not very predictive. It's just the prediction is simply that the neutrino mixing are larger, order 1. Okay, so if we accept that this, considering that the θ13 angle is order 0.1, so a little small, but not that small, and the present data do not still give us a definite, I mean, we cannot conclude that there are more complex structures there, so like try by maximal mixing or things like that. So the atmospheric angle maybe not really exactly 45 degrees and so on. If we just accept that those are order 1 numbers, this paradigm can trivially address such a kind of anarchical neutrino mass matrix. And then, of course, the charged leptons, since charged leptons instead are hierarchical, their masses are hierarchical, the hierarchy can be taken care of by suitable charge assignments just for the right-handed leptons. Okay, so here our idea is to consider a local U1 symmetry, okay? So we gauge it. As you can see, these charge assignments are actually anomalous, okay? But people have shown that there are suitable UV completions where the gauge anomalies can be canceled. So we believe that. We don't build a specific UV complete model, okay? So we just assume that this sector of the theory takes care of that, so it's anomaly free, and so we can have a local U1. So you understand then below that cutoff lambda, besides the standard model field, we are just adding 2 new particles. So we have this scalar, this flavor Higgs that breaks the symmetry, and of course, its radial component, just like the standard model Higgs, will be a real scalar that's it's a physical particle. The Goldstone boson will provide the longitudinal component of the other light particles that we have below the cutoff, which is the gauge boson, the U1 gauge boson, that here we call it just Z prime. If you want, it's a Frogatt-Nielsen Z prime. So their masses then, of course, will be proportional to the symmetry breaking VEV. The scalar will depend on a Courting coupling, on the self Courting coupling in the scalar potential, and of course the mass of the Z prime will be given by the product of the VEV and this a new gauge coupling, so the gauge coupling of this new U1. And both fields, of course, by construction, couple to standard model fermions. The scalar, of course, couples because these operators needs to give us our Yukawa couplings. So one of these VEV can be, if you want, exchange for a physical excitation. So then you see that you get interaction like this. So this flavon couples to standard model fermions proportional to their mass, like a Higgs, and with the coupling suppressed by the U1 breaking the scale. So with an interaction that is similar, if you want, to a axion-like interaction. While, of course, the Z prime will just couple to left-handed, right-handed current, or if you prefer vector and axial vector currents, and the coupling will just be given by the symmetry, so proportional to the charges and the gauge coupling. Okay. So the interesting thing is that both fields are produced in the early universe by thermal interactions because as I mentioned, the idea is that they couple to these UV fields that live at the scale lambda with order one interactions. So basically, they are kept in equilibrium with fields that are charged under the standard model gauge interactions. Okay, so they will be produced thermally in the early universe. They can also be produced actually by decays of cosmic strings. So you have anyway a population of these fields. So for later purposes, I just and of course they will, if they will decay into standard model fermions if those decays are kinematically allowed, of course. So we will have to check their lifetime such that they don't affect BBN. Okay, so we will require these fields to decay before BBN sets on, so order second or 0.1 seconds. Okay, the interesting thing about this flavored Z prime is that by construction is flavor violating. Okay, so if I expand these interactions, so I write them explicitly for up quarks, down quarks, and so on, we see that the interactions are proportional to the charges, of course, to the U1 charges of the standard model fermions. And once you rotate the fields into the mass basis, these couplings are not diagonal, are not flavor conserving. Because by construction, the charges must be different for different generations. So the unitary rotation do not drop. So actually you get flavor violating interactions which are proportional to differences of U1 charges. So this Z prime will mediate at 3-level flavor change in neutral currents, lepton flavor violation, and processes like that. For instance, here is a diagram that shows how it mediates KK bar mixing, or if the Z prime is light enough, and you see, it may be much lighter actually than the U1 breaking scale if this gauge coupling is small. Then you can have also the situation in which mesons or leptons decay into it, like this example, B2K Z prime. And then the Z prime, depending on its lifetime, may be invisible for a detector, so it may be long-lived on the detector scale, or may decay back into it, for instance, into leptons. So this is the most interesting case because it gives the strongest constraints. So for instance, this is the formula that shows the branching ratios of K to pi into Z prime. And so as you can see, it really resemble the decay, the flavor violating decay of a meson into a light axion-like particle, because you see here is just suppressed by 1 over here. The gauge coupling actually drop in this formula, right? So it's the decay, the width is just suppressed by the scale, the U1 breaking scale squared. Just like just like the kaon decay into a pion and an axion, which is just suppressed by the axion decay constant square because it comes from dimension 5 operators. And similar, you can do the same thing for lepton flavor violating decays into this light Z prime, mu to E, tau to mu, and so on. So all in all, we can collect already existing limits from flavor experiments based on the known observation on meson decaying into something light and exotic, or leptons decaying into something light and exotic. So depending on the mass of this Z prime, of course, different processes will be kinematically open or not. And depending on the coupling, the Z prime is long-lived or not. So the best constraint may be due to visible decay, like this one, B2K into B2K and 2 leptons, or by searches for K to pi plus light invisible particle. So as you can see, these already can set quite strong constraints on the parameter space. Here I'm plotting the U1 coupling mass versus the Z prime mass. Okay, as you can see, we can go down to exclude the coupling below larger than 10 to the minus 13 even. And but of course, again, in this plane, all these bounds can actually be rephrased just as a limit on the U1 breaking scale. Of course, the Z prime mass matter just because it will tell you what is kinematically allowed and what is not. And there is this interplay between visible decays and invisible decays. So all in all, depending on this Z prime mass, if these kind of decays are allowed, are open, so you see the constraint on the scale where you break your flavor symmetry is already can be already quite large. So up to order 10 to the 11 GeV in the best case, the one from kaon decays. Of course, if the Z prime is heavy, these decays are off shell, so they're suppressed. So then the best constraint comes from K-bar mixing, and you will get a quite weaker constraint, but still way beyond the energies that we directly probed at Collider. So as you can see, we don't have this symmetry cannot be broken at a scale which is lower than order 10 to the 6 GeV in the best case. But so you see, flavor processes can already test the excluded low to intermediate scales. Okay, but what if this U1 breaking occurs at even higher energies, close to the gut scale or something like that? So fortunately now, as you know, we have a new way to test phenomena that happened at very high energies. So I mean, it's in the very early universe, and it's through gravitational waves. So the idea is that U1 breaking the phase transition connected to this flavor U1 breaking induce the production of cosmic strings. This cosmic strings network emits gravitational waves. One can observe, can constrain them, searching for a stochastic gravitational wave background. Okay. Of course, here there are some assumptions, if you want some strong assumption. This is only possible, of course, if you indeed have a phase transition. So if after inflation, the reheating temperature is, of course, larger than the breaking scale. Okay, so you have a phase in the early universe where this U1 is actually unbroken. Then when the temperature reaches the breaking scale, we assume ordinary second order phase transition, so nothing too dramatic, but that's enough, of course, for the formation of gauge strings. So if that's the case, under this assumption, then we can study the cosmic strings from this model in a way similar to what you do for any of such any cosmological defect of such a U1 you kind of U1 model. So you write the equations of motion and you are looking for solutions which are static, cylindrically symmetric, so meaning strings. So what you get is then something like that. Indeed, you can find solutions of this way, of the classical equations of motion. Here I'm plotting the profile of the scalar field normalized by its bev versus a radial coordinate. Okay, so these cosmic strings then have basically that at the center of this cylindrically symmetric object, in a way the symmetry is restored, the field goes to zero, and then going out, we reach the value, which is the constant value, so meaning the vacuum expectation value of the field outside. And you can define a string width, so the physical width of this object, depending on where it crosses this line here. And this depends basically, there is a mild dependence on this parameter beta. So this is why I have different curves here, which is just the ratio of the scalar, so our flavon mass and the Z prime mass squared, or if you prefer, the ratio of the scalar Cortin coupling over the gauge coupling squared. So these control the width of the string and also the tension. So basically, we can find a numerical solutions for this function g and alpha that tells us that the radial profile of the fields. And with that, calculating the width and the tension of the string in terms of a function that depends on this ratio beta, but they are relatively slow in varying functions. So you see here over 6 order of magnitude, they just change by 1 order of magnitude or less. Okay. So basically you have that besides these numerical factors, the width of the string is inversely proportional to the mass of the scalar field, and of course the tension is proportional to the vev of to the U1 breaking vev squared, which is the important thing here. So the energy per unit length, so the tension grows quadratically with the scale that breaks the symmetry. Okay. So then the strings that has been created, well, they will form a sort of network. So they will crossing, they will form cusps and loops. And so there are then these features that emit gravitational waves. Okay, so especially the loops, they emit gravitational waves, so they lose energies through gravitational wave emission, so then they shrink. And if you go to look at the gravitational wave background that you obtain, so this is the spectrum, the frequency spectrum. The amplitude is proportional to the tension squared. So this means that the signal will be much larger for higher U1 breaking scale. So it actually grows like the force power of the symmetry breaking scale. So you see already that here we can have an interplay with the flavor observables that instead will, sorry? Okay. The flavor observables that instead will can test low or intermediate scales, gravitational waves, of course, uh, as usual, are more sensitive to high scales. So here there are two examples of the gravitational wave spectrum that you obtain for well, two benchmarks. So where we set the parameters, so the mass of the Z prime, the gauge coupling to some suitable values. And in particular, you see here the signal is much larger because this second benchmark has got a larger correspond to a larger U1 breaking scale. Here there is a number of future gravitational wave observatories like Einstein telescopes, BBO, and LISA, and others. One thing that we paid attention to is to include in the analysis the energy losses through particle emission. So if you don't do that, basically the spectrum would look like this dashed line. But instead, if you consider the fact that these string loops below a certain critical size basically will emit light particles, Z primes, for instance, much more effectively than a gravitational wave. So they will lose energy emitting particles and not gravitational waves. So when the loops go below this scale that basically depends on the width. So this cutoff is more important if you have a large, a sort of fat string with a large width, which means if your scalar field is light. So you're not going to emit then gravitational waves below a certain wavelength, so which means that you cut off the signal at higher frequencies, like we show in this plot. So we chose the two benchmarks precisely to show that, okay, if the signal is very strong, then this does not change much. But for a weaker signal, so for a lower scale, this may affect the detectability of the gravitational waves at future experiments. For instance, you see naively, this first benchmark would be within the reach of Einstein telescope, but taking into account this effect, it is actually not. And I'm almost running out of time, but I'm also summarizing because now we can basically put together what we learn from flavor and what we may learn from gravitational waves. So again, here for a given benchmark of this parameter beta, here I'm just taking the Z prime mass equal to the scalar mass. So as a function of the Z prime mass, and the gauge coupling, I'm showing again the part of the parameter space that is already excluded by flavor observables. And these colored regions are the future sensitivity of these three gravitational wave observatories, taking into account this effect here, this high energy, high frequency cutoff, because otherwise the colored region would be would have a better sensitivity on the parameter space, so that they would reach these dashed lines. And here I'm excluding also this part of the plane is excluded by BBN. So in this case, the flavon, so the scalars are the same mass as the Z prime, so it cannot decay into the Z prime, so it's kind of long-lived. You see this feature because, as I mentioned, it couples to the fermions proportional to their mass. So when you cross some kinematic thresholds, when it cannot anymore decay into heavier fermions, to which the coupling is large, then there is an increase in its lifetime. So you see, all in all, the BBN, the flavor, basically close the parameter space for in this corner when the Z prime mass gets small, order GV, and then the gravitational waves test high symmetry breaking scale. The flavor processes low or intermediate scales. So basically, they are complementary in testing this parameter space, and only a relatively narrow area, a relatively narrow region will be unconstrained. So this is the same for another benchmark where we have actually the scalar, which is substantially heavier than the Z prime. So it can decay into it. So the BBN constraint is just given by the lifetime of the Z prime itself, and also the gravitational waves sensitivity is a little bit stronger. Okay, so this brings me to my conclusions. We don't know whether behind the flavor stack sector of the standard model there is some new dynamics. But if this is the case, such a dynamics may live at energy scale that are not accessible at laboratory experiments. So, like for many other, like for GATT models or seesaw models, also in this context, now we have a new window open to what may have happened at such large energy scale. So this is a good thing. And in particular example, for instance, we have shown that there is this very nice interplay, because flavor processes, basically depending on the mass of this Z prime, exclude scales that are lower than 10 to the 6 GeV, or even up to 10 to the 11 GeV if the Z prime is light, while future gravitational waves will exclude scales, will set a lower bound on the same scale, on the flavor breaking scale. So Einstein telescope already, here we have contours for the VEV2, so you can see that Einstein telescope even may go down to 10 to the 11 GeV. And in the very, very long run, projects like BBO even down to 10 to the 9 GeV. So at least for certain scenarios, this can really close the gap and test fully this model. But yeah, you need to be here in a situation where the Z prime is light, and maybe you may not like it. The U1 gauge coupling is pretty small. And this is it. Thank you for